Okay, so we're going to start the exponential and logarithm units. So first we will look at exponential functions, and we'll look at the properties of the graphs, and also a little bit of evaluating exponential functions. So any equation that is in the form y equals a to the x would be an exponential function. So the variable is the exponent, and that makes it an exponential function. So if we want to graph the function f of x equals 2 to the power x, we could just make a table of values and just pick some values to put in that equation. So I'll pick a couple of negative numbers and a couple of positive numbers. So 2 to the 0, anything to the 0 is 1. 2 to the 1 is 2, and 2 to the 2 is 4, and so on. So if we plotted those points, we have 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. I could do 2 to the 3, that would be 8. And so it gets, make sure I put it in the right spot, it gets very steep very fast. 2 to the negative 1, if we remember negative exponents, that would be the same as 1 over 2, and 2 to the negative 2 would be the same as 1 over 4. So we've got a half, a quarter. So as we go in the negative direction, that fraction is going to get smaller and smaller and smaller. And it will never get to 0, because we can never have a base to a power and get either 0 or a negative value. So that fraction would just get smaller. So a half, a quarter, an eighth, 1 over 16, 1 over 32, and so on. And so we have an increasing function because it is going up from left to right. Let's just label it. It has a y-intercept at 0, 1. It has a horizontal asymptote. Because the curve approaches the x-axis but does not touch it. So that would be considered a horizontal asymptote. Or we could say the equation is y equals 0 of the x-axis. And we can also state the domain and range. So the domain would be any real number, because we can use any value for x. The range would be limited. We're not going to get to 0, so we would say y is going to be any number that is greater than 0. So it will never reach 0, but it will get close to 0 as we approach negative infinity. If we wanted to graph y equals 1/2 to the power x, again we can make a table of values. And let's just use the same numbers. Oops, that's a 1. And we'll find these values. So 1/2 to the 0 is still 1. Now we have 1/2 to the power 1, and we have 1/2 to the power 2, which is 1/4. So as we go to the right, we get a half, a quarter, an eighth, a 16th, and so on. So this time the curve would be approaching the x-axis in the positive direction. And then 1/2 to the negative 1, well, when we have a fraction to a negative exponent, we can just flip the fraction, so that would be 2. And then 1/2 to the negative 2 would be 4. So when we change the base to a half, we've gone from an increasing function to a decreasing function. Now it's going down from left to right. The y-intercept is still 0, 1. We still have a horizontal asymptote being the x-axis, or y equals 0. And we still have the domain and range. We still have any real number for x, and we still have any number for y that is greater than 0 or positive. So the only thing that has changed by changing that base is that we've gone from an increasing function to a decreasing function. Everything else stays the same. We can also look at transformations of exponential functions. So in this question, it asks you, oh, let's look at these first. So this question asks you to graph 3 to the power x, 1/3 to the power x, 2/3 to the power x, and 3/2 to the power x. So we could use a table of values, we can sketch them on the same axis, we can look at the similarities and the differences between these functions. So I'm just going to plot them right onto the curve. Let's do 3 to the x in blue. So 3 to the power x, 3 to the 0 is 1, 3 to the power 1 is 3, 3 to the power 2 is 9. So 3, 6. Let's make that 3, 6, 9. So it's up here. 3 to the negative 1 would be a third, and that would be a ninth, and so on. So go down like this, and that would be 3 to the power x. If I were doing 1/3 to the power x, similar to 2 and 1/2, we would have 1/3 to the zeros, still 1. We've got 1/3 to the power 1 is a third, 1/3 to the power 2 is a ninth, and so on. So it will be approaching the x-axis. We would have 1/3 to the power negative 1 is 3, and we would have 1/3 to the power negative 2 is 9. So similar to 2 to the x and 1/2 to the x, the only thing that changes with the graphs is that we go from increasing to decreasing. What if we had 2/3 x? So let's make a table of values, because we might not be sure about this. So let's make a table of values. So 2/3 to the power 1, or to the power 0 is 1. 2/3 to the power 1 is 2/3. 2/3 to the power 2 would be 4/9. Let's use a different color. So we've got 0, 1. We've got 1 and 2/3, which is about there. We've got 2 and 4/9, which is just below a half. And then we'd have 2/3 to the power negative 1 would be 3/2. So at negative 1, it's at 1.5. And then 2/3 to the negative 2 would be 9/4. So that's what, 2 and a bit. So 2 and a bit. Okay, so again, because the base is less than 1, it's going to be decreasing. But it will be a little less steep than the 1/3. Okay, so that's let's start to look at the similarities. So 3 to the x is an increasing function, and 1/3 to the x and 2/3 to the x are decreasing functions. So that's a difference between the two. 3/2 to the power x, so let's make a table of values for that. So this is going to be 3/2 to the x. This one was 2/3 to the power x, so we'll use the same values. I'm just going to change color on these ones. Okay, let's go back to blue. Okay, so 3/2 to the power 0 is 1. 3/2 to the power 1 is 3/2. Squared is 9/4. And then 3/2 to the negative 1 would be 2/3. And to the negative 2 would be 4/9. So let's do this one in yellow. So we have 0, 1. We have 1 and 1.5. We have 2 and 2 and a bit, so let's put it there. And then on the other side, we have 2/3, about there and there. So this is 3/2 to the power x. So 3/2 to the power x is the same as 1.5. So you'll notice that when we have 1.5 to the power x and 3 to the power x, we get a increasing function. And that's because the base is greater than 1. We get a decreasing function when the base is between 0 and 1, so when it's a fraction or a decimal. So we might call the first two growth. Sometimes we call those growth because they are growing, and sometimes we call these ones decay. But the difference is that they will have an increasing function or a decreasing function. What are some of the similarities? Well, they all have a y-intercept of 0, 1. That still stays the same. They all have the same domain, any real number. They all have the same range. Y is greater than 0. We may look at the steepness. So you'll notice that in the increasing functions, if the base is 3 and compared to 1.5, 3 is a steeper graph because the base is bigger. And then on the other way, we have 1/3 and 2/3. 2/3 is a smaller or a bigger decimal, so it makes it a less steep graph. So those are just some similarities and difference between exponential functions. If we look at b, we have y equals -2 to the 1/2 x plus 3. So this has a vertical shift up 3. It has a transformation applied to the x, the half. So the half is going to be a stretch or compression. And remember, it's going to be the opposite. So it will be factor 2. So the half is going to make it a factor 2. And then we have a negative, which is outside the function, so there are no brackets. So the reflection would be vertical. Let's just put vertical reflection here. So it would be a vertical reflection in the x-axis. So I would expect the graph to go up 3, flip over, so flip over vertically, and then we have a horizontal stretch of 2. Okay, let's look at one more. One thing to look for is C. We may have to do a little bit of adjustment with this one. Because the exponent has both a reflection and a shift, we need to separate them a little bit. So the third goes out front, so that's a vertical compression. But we're going to factor out a negative because we want the reflection to be separate from the shift. So the shift is actually up, or the horizontal shift is actually left 2. So we have a vertical stretch of 1/3, or a compression because it's a fraction. We have a reflection horizontally, so it's going to be in the y-axis. And we have a horizontal shift, and it is going to go left 2. So if we look at let's have a look at the graph. So here we can see that it has shifted up 3. it has reflected over that horizontal asymptote, and then again we could check using our mapping notation to see what's happened to a particular point, maybe the y-intercept at 0, 1. So the mapping notation would be that the x is going to be double and the y will be negative and then plus 3. Okay, so the negative sign, the reflection applies to the y, so does the vertical shift. The horizontal is a stretch of 2, so we could pick a point 0, 1, which we know is on the original graph. We're going to double the x, so that would still be 0, and then we're going to do negative 1 plus 3, which is 2, and then we're just going to check. Sorry, that's negative 2. And then we'll check, and yes, or sorry, it is positive 2, my bad. It is at 0, 2. I was looking at the wrong thing. So yes, that point, if we apply that mapping notation to that 0, 1, we do get the point 0, 2, and that's exactly where it is. Graph. I think it's on the next page. So here's the graph. Let's make it a bit bigger so we can see that it has the vertical, there is no vertical shift. So you can see that the horizontal asymptote is still approaching 0. We have a reflection, so that is obvious. The reflection is in the y-axis, so instead of increasing, it's now decreasing. It has been vertically compressed by a third, and it has been horizontally shifted left too. That might not be so clear, so let's do mapping notation. So horizontally, we are applying the negative to the x, and we are going left 2. So we're going to subtract 2, and then the y will be a third. So if we take that 0.01 that we were using, the shift left 2, the negative is still going to remain as 0, and then we're going to shift left 2, so it'll be at negative 2, and then the y will be 1/3 of 1, so 1/3, and so that's left 2 up 1/3, which is approximately there. So that confirms that we did have, in fact, a horizontal shift left 2, and we had a horizontal reflection in the y-axis. Another thing we could do is match curves. So let's look at these a little bit. So we have the equations up here, and we want to match them with the graph. So when I'm looking at these exponential equations, I can see that they've all been shifted up 2. So that's really not much different. So both 1, 2, 3, and 4 all have a vertical asymptote at 2, and so that is consistent with the equations. So then we just have to think, well, how can we narrow this down a bit? I notice that A and D do not have vertical reflections, while B and C do. So B and C have both been reflected vertically, and A and D have not. There are no horizontals, so I'm going to, or there is one here. So let's rewrite this one. We'll factor out the negative, makes that a +2. So this graph, I'm thinking, is either 3 or 4. So I'm thinking A and D are 3 and 4 because they don't have a vertical reflection, and B and C do have a vertical reflection, so I'm thinking those are 1 and 2. So if I were doing A, my mapping notation would be negative x and then -2, and then I have a vertical shift up 2. So I'm going to pick a point, 0, 1. So -0 is 0, -2 is -2, and then it should be up 3. So I'm looking for the graph that has not been vertically reflected, and I have a point at -2 and 3. So -2 and 3 is approximately here. On this graph, -2, I don't think that's quite at 3. So let's check the other graph. So let's check D. So D, again, you'd have to factor it a little bit. You'd have to take out the 3 to separate it from the shift. So we're going to factor out 3. So it has a horizontal compression of 1/3, and then we're going left 2, and then the y is going up 2. So again, if we use our 0.01, we can kind of figure out where that is. So 1/3 of 0 is 0, minus 2 is -2, and then 1, 2, oh, well, that one would also be at -2, 3. So that is not going to help us. So the last thing we can look at is the base. So let's just have a look at the bases. So just comparing bases, I would say that one's a little bit steeper. Let's see. Oh, I forgot one thing we're missing is that the negative on the equation A, that's been horizontally reflected. So that means that D has not been horizontally reflected. So that's still going to look like the normal 2 to the power x. A has been horizontally reflected. So this one would be A because it's been horizontally reflected. It's been reflected over the y-axis. And this one is D because it has not been horizontally reflected. So they do both contain the point -2, 3. That's maybe just coincidental. So when I apply the mapping notation, I do get the point -2, 3 for both, but the difference is that A has been horizontally reflected and D has not. And then we would narrow down B and C to the last two. They have been vertically reflected. They do both have a vertical shift of 2. I would say that 8, you might have to change that to base 2. Or maybe not. So C, let's write it down here. So B, the mapping notation for B, let's see. So B has a horizontal stretch of 2. It's 1/2 x, so it would be horizontally stretched by 2. So we'll write that here. Sorry, my pen's not working great. So it's horizontally stretched by 2, and then it has been vertically reflected and shifted up 2. So it's been vertically reflected and shifted up 2. And so I'm going to just use that with 0.01. If 0.1 is not a great point, you can also use another point. That's just an easy one to use, but we could also certainly use a different point. If it doesn't distinguish between the two, we could also try another point. So 2 times 0 is 0, -1 plus 2 is 1. I think my pen is running out of battery. Okay, back to this. Sorry, my pen died. So 2 times 0 is 0. -1 plus 2 would be 1. So we're looking for the graph that passes through 0, 1, reflected vertically. Well, it looks like they both pass through 0, 1, so that's not going to help us. And they both reflected vertically. So what was the other equation? The other equation also has to go vertically compressed by 1/2. And so I would say that this is B and this is C, because this one is steeper and the base is bigger. So that would result in a steeper graph. Okay, one last thing we want to look at is solving exponential functions. So in grade 11, you would have solved these exponential equations by changing to the same base. When we get through logarithms, we won't need to do that. But for now, if we are reviewing, we would always change to the same base. So for example, we have 1 over 5 to the power x equals 125. So I know that 125 is a multiple of 3, so I could write that as a power of 5, sorry, a multiple of 5. So I would change that to 5 to the power 3. I'd also want to bring the 5 to the numerator on the left, so we'll change that to 5 to the negative 1. And then that would be 5 to the negative x equals 5 to the 3. Once you have the bases equal, then you can drop the base and just work with the exponent. So that means that negative x must equal 3 or x must equal negative 3. Let's do b. So we have 7 to the x plus 2 is 1 over 49. So again, we want to change the same base. I know 49 is a multiple of 7. It's 7 to the 2. So let's write that. And then I would want to bring that up as 7 to the negative 2. Once I have the same base, I can eliminate the base and just work with the exponent. So x would equal negative 4. C, we might have to change both sides to the same base. So 27 is not a multiple of 9, so I would always check smaller. So they are both multiples of 3. So I'm going to change 9 to 3 to the power 2. And then 27 to 3 to the power 3. Now here we have to make sure that we apply the power rule. So we're going to multiply 2 by x and 2 times negative 3. So don't forget to multiply both terms. So 2x minus 6 equals 3 to the power 3. Once we have that same base, we can eliminate the base, just work with the exponent. And so x would equal 9 over 2. D, we have 4 to the power 3 minus 5x equals 1. When you have a 1, you can pretty much change 1 to any base, because remember that anything to the power 0 equals 1. So I'm going to change it to the base that I want. I want it to be 4, so I'm going to change it 4 to the 0. And that means that that has a value of 1. Once I have that same base, I can drop the base and work with the exponents. And so x will equal 3 over 5. So that's just something to watch out for when it equals 1. I'm just going to skip down to f. So f says 1 over 25 x to the negative 1 equals the square root of 125. Okay, so 125 and 125 are both multiples of 5. So 125 is 5 to the power 3. And 25 is 5 to the power 2. So we'll do that first. And then I want to bring the 5 to the power 2 to the numerator, so let's make that 5 to the power negative 2. And remember that root we can write as a rational exponent, so it's root 2 to the power 1. So we could write that as 5 to the power 3, and then change the square root to 1/2. Don't forget to multiply both terms by the negative 2. So that would be negative 2x plus 2, and that would be 5 to the 3 over 2. Now that I have the same base, I can eliminate the base and just work with the exponents. So it'd be 3 over 2 minus 2, which is negative 1/2. So now I can just do both sides by negative, so 2x equals 1/2. So x is 1/2 divided by 2, or 1/2 times 1/2, which is 1 over 4. So roots might appear, change them back to rational exponents. Let's do one more. We'll do g. So g is 8. Let's see, 8 to the power x plus 1. That is inside the square roots. And that is equal to 1 over 32. So 8 and 32 are both multiples of 2. So I'll change 8 to 2 to the power 3. And I'll change 32 to 2 to the power 5. We will multiply the 3 by both terms. So it'll be 2 to the power 3x plus 3. I'm going to bring the 2 to the power to the numerator, so it'll be negative 5. And then finally, I will change the square root to a rational exponent of 1/2. And then I'll apply the power rule again. So it's 3x times a half is 3 over 2x, and it's 5 times a half is 5 over 2. Now we have the same base, so we can drop that exponent. And now we just need to solve for x. So 3 over 2x, I've got negative 5 minus 5 over 2. So we can change the 5 to 10 over 2. So that gives me negative 15 over 2. And then perhaps I'll just cross multiply, might be the easiest thing to do. And so x will equal negative 5.